Have you ever wondered why ice melts or why water boils? Let's get to the bottom of this hot topic. Heat, my friends, is more than just a sensation that makes us crave for a refreshing lemonade or a cool dip in the pool on a sunny day. It's a fascinating phenomenon that plays a fundamental role in our daily lives and the world around us. From the simple act of melting ice to the complex mechanisms of global warming, heat has a hand in it all. In this exciting thermal journey, we will delve into the intriguing world of heat and its effects on the three states of matter: solid, liquid, and gas. We will unravel the mysteries of how heat is generated and transmitted, and explore the profound impact it has on natural processes. So buckle up as we embark on this thermal journey. Imagine particles as people at a party. What happens when the music, or in our case heat, turns up? Let's start with solid particles. They're like the wallflowers at our party. They're tightly packed together, vibrating in place, not really making any daring moves. But when the heat turns up, they start to vibrate more and more. It's as if the beat of the music is getting faster and they can't help but shake a bit more in their spots. But remember, they're wallflowers, so they're still not straying too far from their original positions. Now let's turn our gaze to the liquid particles. They're the social butterflies of our party. They're free to move around and mingle with their fellow particles, but they still stay relatively close to each other. When the heat cranks up, these particles move faster and start to spread out a little more. They're like dancers who've just heard their favorite song. They can't help but move and groove a little more enthusiastically. Last but not least, meet the gas particles. They're the wild ones, the life of the party. They move around quickly and freely, covering every corner of the room. When the heat or the music in our analogy gets turned up, these guys really let loose. They move even faster and spread out as much as they can. They're like the party-goers who are having such a great time. They end up dancing on the tables and the couches, making the most of all the available space. So to sum it up, the more heat you add, the more our particle party-goers move. Solids start to vibrate more, liquids move and spread out a bit more, and gases, well, they just go wild. It's all a lively dance of particles, choreographed by heat. So next time you're at a party, remember you're just like a particle in a heated system. Now let's turn up the heat, but where does this heat come from? It's a question that might make you sweat if you don't know the answer, but don't worry, we've got it covered. Heat is the ultimate social butterfly. It loves to mingle and move from one place to another, but before it can do that, it has to be created. So, how does that happen? Let's start with something simple: friction. You know when you rub your hands together really fast and they start to feel warm? That's friction at work, transforming your kinetic energy into heat. It's the same reason why a matchstick lights up when you strike it against the side of the matchbox. The friction between the matchstick and the rough surface generates enough heat to ignite the match head. But what about the heat that keeps our planet warm and toasty? That's where things get a little more complex. The sun, our primary source of heat, generates its warmth through nuclear reactions. In the sun's core, hydrogen atoms collide at such high speeds that they fuse together to create helium. This process, known as nuclear fusion, releases a massive amount of heat and light. It's like the universe's most epic dance party, where hydrogen atoms are the guests, and the massive release of energy is the disco ball. Then there's geothermal heat, the warmth that comes from deep within the Earth's crust. It's produced by the slow decay of radioactive particles present since the formation of the planet. It's Mother Nature's own underfloor heating system. And let's not forget about chemical reactions. When certain chemicals interact, they can release or absorb heat. Think about hand warmers. They contain a supersaturated solution of sodium acetate. When you snap the metal disc inside, it triggers a chemical reaction that releases heat. So, heat is everywhere. From rubbing your hands together to the core of the sun. Pretty hot, huh? Did you ever wonder why a metal spoon in a hot soup can burn your hand? Let's stir things up. Imagine you're cooking up a storm in the kitchen. You dip a metal spoon into a pot of simmering soup and suddenly, yowza! The spoon handle is scorching hot. This, my friends, is a prime example of heat transmission through conduction. Conduction is the process where heat is transferred from a high-temperature region to a low-temperature region through direct contact. It's like the latest gossip in a small town rapidly spreading from one person to the next. When the atoms in the hot part of a material get excited, they start vibrating faster. This increased energy is then passed on to their neighboring atoms, like a high-stakes game of hot potato. Metals are excellent conductors because they have free electrons that can move around easily, carrying thermal energy with them. So, when you stick a metal spoon in hot soup, the heat swiftly travels up the spoon and onto your unsuspecting hand. Ouch! Now, conduction doesn't just occur in your kitchen, it's also responsible for some pretty cool natural processes. Ever noticed how the ground heats up on a sunny day? That's conduction at work. The sun's rays heat the ground, which then transfers the heat to the air molecules in direct contact with it. Even our own bodies use conduction. When you hold an ice cube, it feels cold because it's absorbing heat from your hand and melting. The heat from your hand is conducted to the ice, causing it to change from a solid to a liquid state. And what about animals in cold climates, like polar bears? Their thick fur and fat layers act as insulators, slowing down the conduction process and keeping them warm despite the icy temperatures. So, that's why chefs prefer wooden spoons over metal ones. Don't want a hot surprise, do we? Ever wonder why it's colder at the top of a mountain than at sea level? Let's ascend this thermal peak. Picture this. You're boiling a pot of water for a nice cup of tea. As the water heats up, the particles at the bottom of the pot get excited. They start to dance around faster and faster, spreading apart and becoming less dense. As a result, they rise to the top, pushing the cooler, denser particles down to take their place. This cycle of hot rising and cool sinking creates a circular motion known as convection. Convection is the main method of heat transfer in liquids and gases. It's like a thermal version of musical chairs. When the music, or in this case the heat, starts, the particles scramble, moving around until the heat stops and they settle into a new spot. But convection isn't just confined to your kitchen, it's happening all around us, shaping our world in ways you might not even realize. Ever notice how seabirds seem to glide effortlessly on air currents? That's convection at work. The sun heats up the surface of the earth, which in turn heats up the air above it. This warm air rises, creating updrafts that seabirds can ride like invisible roller coasters. And then there's the weather. Ever heard of a low-pressure system, or a high-pressure system? These are caused by convection. When warm air rises, it creates a low-pressure area below it. Cooler air rushes in to fill the void, often bringing with it clouds and precipitation. Now let's circle back to our mountain. The air at the base of the mountain is warmer because it's closer to the heated surface of the earth. As this warm air rises, it cools and becomes less dense, leading to that chilly mountaintop air. So the next time you're shivering on a mountaintop, remember it's because heat decided to take an elevator ride. Why do you feel warmer when you step into sunlight? Let's shed some light on this. Now, we're not talking about radioactive mutants or superhero origin stories, but the radiation we're discussing today is just as fascinating. Radiation, in the context of heat transfer, is a method of energy transmission that doesn't need any medium, like air or water, to travel. It's like the VIP of heat transfer methods. It doesn't need a ticket or even a road. It just goes where it wants to. This is how the sun, that giant, flaming ball of gas millions of miles away, manages to keep us toasty here on Earth. The sun's radiation reaches different surfaces on Earth, and here's where things get interesting. Different surfaces react differently to the sun's rays. A black asphalt road, for example, absorbs most of the radiation, gets heated up, and then you get to experience the joy of hopping around on hot tarmac. Meanwhile, lighter surfaces like a sandy beach reflect more radiation, so they don't heat up as much. It's like the cool kid in school who never seems to break a sweat. This absorbed heat from the sun doesn't just make our summers enjoyable or unbearable, depending on who you ask. It plays a crucial role in regulating Earth's temperature. During the day, the Earth absorbs the sun's radiation, warming up the surface. At night, the Earth cools down as it radiates this heat back into space. It's a beautiful cosmic dance of heating and cooling, but here's a twist. Not all the heat radiated by Earth makes it back into space. Some of it gets trapped by our atmosphere, which acts like a cozy blanket keeping us warm. This is what makes life on Earth possible. Too little heat and we'd be a frozen wasteland. Too much, and well, we'd be a literal hot mess. So, the next time you're basking in the sun, remember you're enjoying a direct delivery of heat. It's a silent, invisible process happening right above your head and beneath your feet, but its effects are as real as the warmth you feel on a sunny day. Have you heard about the greenhouse effect? Let's clear the air on this one. The greenhouse effect is a natural process that warms the Earth's surface. It's like Mother Nature's cozy blanket, keeping our planet habitable. But just like too much of anything isn't good, an excess of this warming can lead to climate change. Greenhouse gases, primarily carbon dioxide and methane, are the main characters in this story. They're like the invisible bouncers of the Earth's atmosphere, controlling the exit of heat radiated from the planet. When the sun's energy reaches the Earth, some of it is reflected back into space and the rest is absorbed. These absorbed rays heat the Earth, which then emits infrared radiation or heat. The greenhouse gases trap some of this heat, preventing it from escaping back into space, and thus warming our planet. Now, where do these greenhouse gases come from? Well, Mother Nature does produce some, but a significant portion comes from us, humans. The burning of fossil fuels for electricity, heat, and transportation is the largest single source of global greenhouse gas emissions. Agriculture, deforestation, and industrial processes are also major contributors. It sounds grim, doesn't it? But hey, don't lose hope. We're not just the problem, we're also the solution. We can reduce our greenhouse gas emissions in so many ways. Switching to renewable energy sources, improving energy efficiency in our homes and vehicles, reducing, reusing, and recycling, and even planting more trees. Here's a fun fact. Did you know that a single tree can absorb as much as 48 pounds of carbon dioxide per year? So imagine if we all planted one tree each. That would be a forest load of carbon dioxide absorbed. And remember, change starts at home. Little things like turning off lights when they're not in use, or choosing to bike or walk instead of using the car for short trips can make a big difference. So remember, every little action counts in keeping our Earth's thermostat healthy.